Okay, now let us look at vectors 4. For vectors 4, we focus on finding the equation of lines and planes. Alright, so we no longer just deal with vectors, for example, position vectors or free vectors itself. Alright, so in chapter vectors 1, okay, we mentioned about a vector OA is actually called a position vector because it is constrained at to a specific point, whereas a vector that's not constrained to a specific point like O, we call it a free vector. Alright, and when it comes to presentation, please be very careful. If you're referring to a vector OA, which is a position vector of A, you have to write OA with an arrow on top to represent that this is actually a vector. And you should not be saying that OA is equals to A, because A is actually a point, meaning that A is written in a coordinate form, for example, 4, minus 2. Alright, so please be very careful with your presentation of vectors from now onwards. Alright, so maybe before I introduce to you the vector equation of a line, let's try to do a simple exercise. Okay, now suppose I have a position vector of A, OA over here, and I have a free vector B. Now, where do you think are this vector R1, R2, R3, R4, R5? Okay, so let's do a quick exercise. So now, where is vector R1? Okay, you will notice R1 is basically the addition of vector OA and B. So for example, this is OA. Now this little arrow here represents B, vector B. So the resultant is going to be this. Okay, so this vector coming up from the origin towards this point is vector R1. Alright, so this is actually a position vector of the point here. Alright, and this point is on the dotted line. Now you can do the same for the rest, and if you do it quickly, you will realize R2, okay, is also a position vector of a point on the line. Alright, and then suppose R3 is OA plus 4 times of B. So suppose this arrow here is 4 times of B, and then you will have a resultant, this. Alright, so this vector in green is your position vector, which represents R3. And then you can do for the rest R4. So suppose this little arrow here is negative B, and then so OA plus negative B will give you this. So this is a position vector of a point on the line again. And the fifth one, R5, okay, again is the position, it will give us the position vector of another point on the line. Okay, so for example this. Now, so can you imagine, okay, if you are to draw many vectors, many position vectors R, which is OA plus lambda B, and lambda can be any real value, what do you think you will get? You're actually going to get all the position vectors of the points on a line. Alright, so this is something that made us suspect maybe the equation of the line is given by this. Alright, so we're going to look at it further. For these questions in the box, you can come back to it later. Okay, so let us try to understand. Now, I'm going to call any point on the line R. Okay, so OR or vector R is going to represent the position vector of any point on the line. Now, I want to try to form some form of vector equation for OR so that I can represent the position vector of any point on a line in terms of A and U. All right, and what is this U? U is basically a vector that is in the direction of AR. And what is A? A is basically a point of the position vector of a point on the line. Okay, so firstly, as I mentioned, U is something that is parallel to AR. So meaning that your AR can be written as lambda U. Okay, and remember the goal is about making R the subject. So I want to try to express the vector R in terms of U and A, and this will lead me to OR is equals to OA plus AR. Now I know what is OA. OA is simply A, and AR is lambda U. So I can actually say that the position vector of R, and R is any point on the line, can be represented as R equals to A plus lambda U. Okay, and therefore this is also known as the vector equation of a line. Okay, where lambda is any real number, A is the position vector of a given point on the line, and U is a direction vector, okay, and which is parallel to the line. Whereas, so all in all, right, R is something that will give us the position vector of all the different points on the line. And so we also call this R equals to A plus lambda U, the vector equation of line L. Now, there is always a common misconception of what is R. You think that R is a line, but R is not a line. Okay, we already mentioned here R is a position vector of different points on the line. All right, so that's something that you have to remember and be very clear about, because past A-level question did ask what is R. All right, so if you say R is a line, then it is not correct. It is actually position vectors of the different points on the line. All right, and be very careful when people ask you for the equation, the vector equation of a line. You cannot just give us A plus lambda U. All right, A plus lambda U is not an equation. An equation should have an equal sign, right? All right, so you must always make sure you write R equals to A plus lambda U. Okay, so recall in O-level, when you're asked for equation of a line, you don't give people 3x plus 2. Okay, you must give y equals to 3x plus 2. Okay. Okay, to help you understand a little bit better, we give you some concrete examples. So for example, if U is this vector, okay, so meaning that the line L is parallel to 3 minus 1, 2, and A is a fixed point on the line with a position vector 0, 3, minus 1, then any point on the line would have a position vector of R equals to A plus lambda U, right? Okay, A plus lambda U. Now, if my lambda is 2, okay, I plug in lambda is 2, and my A is this vector, and my U is this vector, I will get a vector, okay, 6, 1, 3. So what does this 6, 1, 3 means? 6, 1, 3 is a position vector of a point on a line. And this point has coordinate 6, 1, 3. Okay, similarly, when your lambda is minus 1, you plug it into the equation of the line, you get a vector minus 3, 4, minus 3. So what is this? This is actually the position vector of another point on the line with coordinate minus 3, 4, minus 3. All right, so if you're asked to find the position vector of a line, you notice you need a fixed point on the line. So you need to know the position vector of a point on the line, and also you need to know a vector that is parallel to the line. Alright, so two things you need to know before you can form the vector equation of a line.